All right, so let's just talk about the energy of substances. Okay, so energy in substances. So this is a continuation of, I guess, kinetic molecular theory. I think this is what it is. But what we're basically talking about is, and let's use a simple substance. Let's use a monatomic. Let's use a monatomic gas to describe what we're talking about here, or not even a gas. Sorry, just a monatomic substance. It doesn't necessarily have to be a gas. All right, so let's start with this thing in its solid state, right? Wow, that's horrible. Hang on here. Have the tools, let's use them. Okay, so let's say we have this substance and it's in solid form. Oh, solid form, try that again. Okay, so when it's solid, what are its molecules, or sorry, what are its atoms like? Well, probably this happens when it's cold if it's monatomic. If things are monatomic, they're not molecules, and they have probably very little attraction to each other. So very low attraction. Really only van der Waals forces probably would be acting, right? But if we get them cold enough, right, there will be some attraction between them. There has to be, or they wouldn't become solid. So if I think about it, in their solid state, they're probably somewhat regularly arranged, and there's some bonding of some type between them. It's not chemical bonding. In this case, it's that those van der Waals bonds. What's the other word for van der Waals bonds? London dispersion forces. I think that's the name of the force, but the bonds that are formed are called van der Waals bonds. So if you think about it, the energy here is in two forms. These are jiggling, assuming we're above 0 Kelvin. They're jiggling, but they're also attached together much like they would be if you had attached them together with springs. Okay, so as they jiggle one way, you get a potential energy increase, right? Because they're like springs, and then they spring back, and they might, increase. So you can kind of imagine two adjacent molecules as sort of being, or atoms, I should say, as being attached by springs. And you can imagine that there's going to be a fluctuation between potential energy and kinetic energy as they spring back and forth and jiggle, right? So there's sort of two forms of energy going on here. We say then that the internal energy in a solid, and to a lesser extent, but still in a liquid as well, because liquids are held just not quite as stiffly, are made up of two things: some EK and some potential energy in the bonds that you can think of like springs. But once you get to the gas phase, it's different. In the gas phase, especially in an ideal gas like a monatomic gas would be, now there's no attraction between them, right? And they've also massively expanded their distances apart, right? Roughly about 10 times in each degree of freedom. So the volume of a gas then is roughly 10 cubed or 1,000 times the volume of the liquid form or the solid form, okay? So now all the energy in the gas, the internal energy, is all in the form of EK, okay, or kinetic energy. So internal energy of a gas then, since there's no more of this going on, is all equal to the EK. This is important, all right, because we know that EK then is equal to 1/2 mv squared. And we can start to think about some interesting facts. Like, for instance, we know from before that if we were to take the temperature of this gas with a thermometer, that the more EK that it has, the higher the temperature would be. So the temperature then is in direct proportion to EK, right? So temperature is directly proportional to EK. And then we can talk about velocities, right? If we know the masses of these objects, we can talk about velocities. Or if we know how much there is there, then we could talk about all of the energy contained in that gas in the terms of kinetic energy. So we can bring in the concept of moles of gas and how much energy a mole of gas would have. Okay, so we're almost out of time, but I'm going to leave that with you. And this maybe hopefully explains why we generally deal with gases when we're talking about kinetic molecular theory. We don't have to worry about the potential energy inside of here, which adds a little bit of maybe difficulty to the problem. We'll leave it with that.
Give you that